In this video, we want to understand what happens when we do downsampling. So the assumption is we are given a sequence xn, and this sequence came about by sampling a continuous time signal x of t using sampling time t, and we got xn. And we are interested in seeing what happens when we downsample. So we input xn into this downsampling block. We downsample by a factor of m, we get xdn. What is the relationship of xdn? So how is this related? Xdn is related to x of t. In particular, we are interested in knowing the frequency domain aspects of this new discrete sequence. Okay, so first of all, remember the relationship between xn and xt in frequency domain. So if xn comes from sampling a continuous time signal, then the frequency in frequency domain, this dtft is given by multiple copies of the continuous time signal that are, so multiple copies of the continuous time signal, the frequency axis is scaled by t, the multiple copies are shifted by 2 pi, and there is the scaling of amplitude by 1 over t. This is what we have for our original sequence. Now we hope that by downsampling, when we downsample xn by a factor of m, then the equivalent effect is, what we are hoping is the following. We don't do that, but we are hoping that the equivalent effect is as if we are sampling our continuous time signal with the sampling time mt. So we are getting xdn, which is x of nt2, which is xmt. This is our hope. Okay? This is what we want to accomplish. We want to accomplish this using this operation. So the question is, does downsampling really do this? Okay, that is the question that we are interested in asking. And if the downsampling operation was doing this, then we know the relationship between the dtft of xdn and the ctft of x of t. So if xdn is indeed sampled version of x of t with sampling time mt, then we know that in that case the following would be true. xd of e to the j omega, that should be equal to 1 over mt, the new sampling time, k from minus infinity to infinity, x of j little omega minus 2 pi over mt parentheses. Okay, so if xd of n is indeed this case, then this equation should be true. Okay, because we know the relationship between the Fourier transform of a continuous time signal and its samples. So the question is this relationship true? Is xd of n indeed x of mt? Okay, well, checking that is not that difficult. So we see that what we are given is xn, and we downsample it by a factor of m to get xdn, which is by definition keeping every mth sample. So now we simply write xdn, this is equal to x of nm. Well, I can write that as x of l, where l is nm. But what is x of l? So I've just done a change of variables. What is x of l? Well, let's come over here. We know that x of n is x of nt. So since we know that xn was obtained by sampling x of t, we simply use that relationship. So we know that this is simply x of l t, where l equal to nm. And now I plug the value of l, so I get nmt. So I made an error over here. This should be x of nmt. I was missing n before. Okay, so let's compare two things. Let's compare what we wanted, which is this red box. We wanted that xd of n can be written as samples of x of t every mt seconds. And what we get is that when we run xn, the original sequence, through a downsampler, indeed we get that the downsample sequence is nothing but samples of my original signal every mt seconds. So effectively, I have increased the sampling time by a factor of m, or I have reduced the sampling rate by a factor of m. And because of the fact that this red box and this red box are the same thing, this means that the Fourier transform of this sequence xdn should be what I would have obtained if I had actually done sampling of my continuous time signal with sampling period mt. So the upshot of this discussion is the following. When we downsample an already sampled signal where the previous sampling period was t, so when we downsample that by a factor of m, then our new sequence xd has the Fourier transform, which is 1 over mt summation k from minus infinity to infinity xj little omega minus 2 pi k 2 pi k over mt. So there is a 2 pi missing over here also. 2 pi k. Okay. So this is my relationship between my downsample signal and my original continuous time signal's Fourier transform, and it has the same relationship that we know from our basic sampling theory, which is that the dTft of xdn has three properties. The first property is that you scale the frequency axis of the CTFT of xt by a factor of mt. So this is given by, this is the CTFT of your continuous time signal, and you are scaling the frequency axis by a factor of mt. The second property is that you scale the amplitude by 1 over mt. So this is where the second property comes in. And the last property is that you get multiple copies of the frequency and amplitude scaled version of the CTFT, and these copies are shifted by multiples of 2 pi. So this is the aspect of multiple copies. You have summation, infinite copies, and they are shifted by multiples of 2 pi. So this is exactly the same relationship that you would obtain if you had directly sampled a continuous time signal with a sampling period mt. And you see that in that work. In this case, this is just showing that throwing away every m-1 samples gets you back the same thing. So let's see this thing in action. Let's say that you had x of t, and when you sampled it with originally with sampling period t to get xn, there was no aliasing. So let's assume that your signal was originally band limited to pi over t, which is the requirement for no aliasing. Now, what the theorem is saying, or what the discussion that we have done earlier says, is that if I now downsample by a factor of m the sequence to get xdn, then this is what the Fourier transform of my downsampled signal will look like. First of all, I'll get a scaling of the frequency axis, and I'll get multiple copies, and I will get scaling of the amplitude. So I'm going to draw the first copy. Okay, so instead of 1, I get 1 over mt due to scaling of the magnitude. Now, there is a scaling of the frequency axis by mt. So what I will get is pi m. So I will multiply this by this fraction by mt, so I'll get pi m. Similarly, I'll get minus pi m. This is my first copy centered at little omega equal to 0. Now assume, so for the case of for m equal to 2, I will have another copy centered at 2 pi, and that will go up to 0, and then it will go up to 4 pi. Okay. Similarly, I'll have another copy at minus 2 pi. So it will go up to 0 and up to minus 4 pi. So you see, now in this case, what is happening here? If you focus here, this point will end up being pi, and this point will be minus pi. This point should be minus pi m. Okay, so what is happening here? We are indeed getting multiple copies, but we have overlaps of the primary copy and the other copy, and the reason is because effectively we have sampled our effective sampling period is T2 equals to MT. And we know from our basic sampling theory that if my sampling period is MT, or in other words, my sampling frequency is 1 over MT, then I better be band limited to, we want to be band limited to pi over MT. We want to be band limited to pi over the sampling period. Our effective sampling period in this case is MT. So what happened was that originally, even though we had satisfied the Nyquist criterion, because we have increased our sampling period or reduced our sampling rate, in this particular problem that I am showing you, we are violating the sampling theorem condition. Our sampling period is not satisfying the Nyquist criterion. And because of that, what we get is aliasing. Our main copy and the other copies are actually overlapping. But that is no surprise. So we have aliasing in this case because x of t is not band limited to pi over mt. It is only band limited to pi over t. So what that tells you is this following thing. So this is very important in downsampling. When we downsample, we run the risk of aliasing. Okay. The only way to avoid aliasing is to have the original signal band limited to pi over mt. So aliasing in downsampling or decimation can be avoided if x of t is band limited to pi over mt radians per second. Okay. So what happens in that case? Let's take a look at another example. So let's assume that you had a signal whose Fourier transform was as follows. It is band limited to pi over mt. And what you did was, again, you took the signal, originally sampled it by t to get xn, and then you sampled it or downsampled it by a factor of m to get xd of n. If you do that, then what would happen is that you will get, again, multiple copies. Now the scaling will be that you will scale the frequency axis by mt, so this will get multiplied by mt. The amplitude will be 1 over mt. Then you will get another copy at 2 pi, but that copy will only go up to pi. There will be no aliasing. Similarly, another copy at minus 2 pi. And again, you will have no aliasing. And this is what the spectrum of your Fourier transform of the downsampled signal will look like. Okay, so we understand to avoid aliasing in downsampling, the original signal, continuous time signal, must be band limited to pi over mt, or pi over your new sampling rate. We can equivalently talk about where should xn be band limited to, because remember, xn, when we sampled xn by a factor of t, right? So xn will also have a Fourier transform, which will be, so in this case, xm will be pi over m minus pi over m and 1 over t. And similarly, at 2 pi, we'll get another copy. And here is pi. And at minus 2 pi, we get another copy. Okay. This is minus pi. So you see that if xt was band limited to pi over mt, then xn is band limited to pi over n. So another way of saying is that to avoid aliasing, so another condition is aliasing equivalently during downsampling can be avoided if xn is band limited to pi over m. Okay, they are equivalent statements. I can say that the original signal has to be band limited to pi over mt radians per second, or I can say that the discrete signal that we are downsampling is band limited to pi over n radians per sample. They are equivalent statement. Okay, so we'll conclude by reminding of take-home messages. So the first message is that if we take a sequence xn and we downsample it by a factor of m to get xdn, and the sequence that we are downsampling came by sampling a continuous time signal with sampling period t, then the downsample sequence is the same sequence that we would have obtained by sampling xt with sampling period mt. So downsampling operation effectively increases the sampling time by a factor of m, or reduces the sampling rate by a factor of 1 over m. The second message is that the frequency domain relationship between the downsampled signal and the original continuous time signal is the same as in classical sampling theory. We get scaling of the frequency axis by a factor of mt. We get scaling of the amplitude by a factor of 1 over mt. And we get multiple copies that are shifted by multiples of 2 pi. And the last message is that aliasing in the downsampled signal xdn can be avoided if xn is band limited to the original sequence that you downsampled is band limited to pi over m, which is equivalent to saying that the original sequence was band limited to pi over mt. Now, if that were not the case, then we would have to employ actually an anti-aliasing filter in discrete time. That is different from sampling theory, where typically anti-aliasing filters are employed in continuous time. That we will discuss in a later video. But these are the three main take-home messages for downsampling a sequence to get a sequence that gives you a reduced sampling rate.